is Bruno Toaldo from my university, that's Torino University, and he will talk about a semi-Markov integrated end-fire model for neuronal activity. Please, Bruno, we can start.
Okay, can you hear me?
Yes, we do.
Very well. You are probably seeing my slide now?
Yes, we
Very
do.
well. Okay, so the difficult part is done. Okay,
Yes.
so thank you. Thank you to all of you for being here, and thank you to the organizer for giving me the possibility of explaining you something of my work. So my name is Bruno Toaldo. I am in principle a mathematician, but I recently enjoyed the possibility to apply some of the things I am studying from the mathematical point of view to this exciting field, which is neuronal modeling. Okay, so it is thanks to Laura and my co-authors, Giacomo Ascione and Enrica Pierozzi, that I started to believe in this application. The point is, what I work on is concerned with first passes time of random processes, and therefore this probably remind you the possibility to study and to use first passes time of random processes in the context of Leaky integrated end-fire model. Okay, so this is a very easy approach to mathematical modeling in neuroscience. So the idea, the very basic idea, which you certainly know better than me, is to describe the membrane potential of a neuron with some random process. For example, a random process which is a strong solution of an SDE, which is written here on the slide. If you see the arrow of my mouse, probably I can highlight something for you. Because these quantities can have a nice interpretation in this context. So one has that capital VL is the leak potential, theta, the parameter theta is the characteristic time in the RC circuit, and then the leaky part is a locally integrable function which represents the stimuli, the input stimuli. And the random part, so what makes it random is this noise, which is a white noise, and thus W is just a Brownian motion, so linear process. One says that a neuron fires if it emits the signal when the random process capital V cross a fixed or eventually moving boundary, which is capital V of t. Then there are different approaches to what happens later. One can reset and let's start the mechanism from the beginning, or you can move the threshold. So there are different approaches later. But we focus in this talk only on the first part, and then the classical approach are applicable to what I'm saying now. So it is clear that in this framework, the distribution of these random variables, so the first time the process cross the threshold is crucial. And the very historical paper on this started to consider this quantity in 1962, where in some seminal papers by Bernstein, they took, they plotted some neuronal, this quantity, okay, so they plot the histogram of this random variable for after observing some neural units in the Collier nucleus of the cat, and the authors realized that in particular one of these units, which was considered representative, is this histogram is unimodal asymmetric, and clearly its decays was not an exponential. So this means that in order to fit data, one model based on this quantity should be a random process whose first passes time to some threshold as a slow decay, okay? So which is not exponential. And there are several attempts have been made, and there are several approaches in the literature to fit this and this this decay. And some are essentially based on the exponential function, which is in principle apparently not correct. Other on gamma distribution, which is still an object whose decay is exponential, But the most commonly approach is given by the author of the first paper itself, which is Bernstein and Mandelbrot, which is a very historical paper in this topic. And they essentially believe that this decay can be fitted with a stable law. So with power law decay of the distribution, which in principle could be parameterized, okay? Because if it is a power law decay, so a stable law with alpha stable parameter, you can in principle estimate the parameter alpha. So it turns out that in the very classical model described above, the solution to the SDE is a slight modification of an Austin-Uhlenbeck process. So in this case, it can be proved that the intervals between spikes, so fires in the neuron, have an exponential trend. The question is if it is possible to attain a linear model having a very easy model like this, having the same interpretation of the parameters, such that the trend can be fitted to be not exponential. The trend of the distribution, so the tail of the distribution of the fastest time, can be fitted to be not exponential, but some heavy tail distribution with some parameter that you can tune. And the point is that this is my question, but actually most of the literature concerning in more recent years, not related to 1960s, essentially relies on the use of Markov processes. But with Markov processes, the point is that it is very hard to build, in the sense that I've not been able, and as far as I know, it is not easy, it is not possible to get this clear heavy tail behavior for the first passer's time having a parameter. Okay, of course you can have, it is easy to use some Markov processes whose distribution of first passer's time is heavy tail, but it will be not related with the SDE above, and it can be, and you will not have a parameter to tune the curve, to tune the decay. So essentially the reason of the use of Markov processes, my feeling is that the use of Markov processes is therefore due to the easy mathematical approach that can be used to deal with the first passer's time problem. Okay, so if you have a Markov process on some filtered probability space, and you take the exit time of this guy from any set, then this quantity, if you put capital G to be the open interval minus infinity C, then this is the first passer's time to a threshold. Okay, in general, this is a stopping time, and as you can use the theory of stopping time for Markov processes. And so in what follows, I will use the classical notation from Markov processes. Okay, so when you see capital Px and capital Ex, it means that we are conditioning the process to start from here. And with the symbol P capital Tx, we just mean the density of the passage time of Markov process. So I was saying Markov processes have a lot of comfortable properties in the sense of exit times, not only for modeling. And for example, you can estimate the first passage time distribution in very explicit form in some cases. For example, if you have a Brownian motion, you can have an explicit density, even if the Brownian motion is with drift, then you have a closed form for the density of the first passage time. And in the case above, so for example, if you take an Austin-Uhlenbeck process, which is just a bit easier, but it holds also in the more general case, so in the Leaky integrated fire case, the exit time from minus infinity C, so the first passage time to level C of this process, is asymptotically behaves as t to infinity like an exponential. Okay, so we are still in the exponential case. This is not an explicit representation. So this is an asymptotic behavior. But okay, who cares? If it fits data far from zero and close to zero, then one has that more or less the distribution is this way. In general, if you take and Markov processes, a Markov process associated with an SDE, so processes having this form are continuous, have continuous path, in general, you have that they solve that the survival function conditionally to the point x satisfy a PDE. Okay, so this is another reason for which the theory of first passes time of Markov processes is easily to be applicable in this context, because you can essentially solve a PDE numerically if you want to have precise information on this distribution, even if you cannot compute this precisely, explicitly, or you cannot estimate. You know that it satisfies a PDE. So from this PDE, you can get a numerical solution. So you can, in applications for mathematical modeling, approximate this quantity effectively. And the letter A, capital A here is the generator. Okay, so this is something you can obtain starting from the governing SDE. So the idea, our idea is to introduce a model which is very, very close as in the sense of interpretation to the original Leaky integrated fire model, but we introduce a random time change of the model, of the original model, which essentially means that we are making the evolution, the original evolution, faster or slower. Okay, so we are introducing something which makes things faster or slower randomly. Okay, of course, this guy here is not an arbitrary process, but what I will tell you now is how to construct this process. So how to choose this capital L and the possibility that you will have in order to fit your data. This is the idea. So in this case, one has that the solution to this process, to this equation, sorry, is the solution capital V to the original equation, so with no time change, time changed with the random process, capital LT. And this can be stated rigorously, okay? So I didn't put here the rigorous statement, but there is a paper, there are a couple of papers on this. So this is a well-posed SDE with strong solution and everything works well. And what it turns out is that this process here, so the time-changed process is not Markovian, but semi-Markovian. And what does this mean? And what is the distribution of the first exit time are the questions I want to answer now. So what is a semi-Markov process? You know, when you work with Markov processes, in particular in the context of neuronal modeling with continuous processes, so look at the second path. You know that a Markov process, which is in our case is something like an Austin-Uhlenbeck, but in any Markov process can never stay constant and leave the point continuously. Okay, so if a Markov process stays constant, then it must stay constant for an exponentially distributed time, and then it must jump away. So it cannot leave a point where it is continuously. If it leaves a point continuously, like Brownian motion, then it is never constant. Okay, so there are no other possibilities. Semi-Markov processes allow this possibility. So essentially, heuristically, the idea is that you can take the class of Markov processes and add these two features, and then you get the class of semi-Markov processes. But of course, when you introduce this possibility, what happens is that imagine that you know all the paths of a process up to a certain time s. So at this time, you know everything about the process, and you want to compute the probability of something in the future. Then the quantity gamma of s, which you are ignoring in the Markov case because of the lack of memory of the exponential distribution, becomes relevant. Becomes relevant because, of course, you don't have exponential time, and thus you are conditioning an exponential random variable to be greater than something, and this is relevant when the waiting time is not an exponential. When it is an exponential, like in the Markov case, you can avoid to consider this. And thus one possibility to define a semi-Markov process is to say that it is Markov together with this coordinate. So if you keep this information together with you and you introduce this quantity gamma of t, then what happens is that the couple here is Markovian. So one says that X is semi-Markov, this is Markov. This is one possibility to define the class of Markov processes. So when you compute probability in the future of some point S, you must keep it with you. So this gamma of S is relevant. So the time change construction, as introduced in the SDE above, can be explained by resorting to a new process, another external process, which is called sigma. Okay, so actually this coordinate here is the most important one, even if we time change with capital L. So in the SDE above, the key quantity is capital L. But it turns out that this capital L is the inverse of another process. So it is easier to introduce the other process and then having the other process, you get your random time. So the external process here is sigma. Imagine that we want to time change capital L. We have a process here which is called sigma, which is increasing and jumping. And when you take the first passage time of this guy here through level t, so it's inverse, the jumps of this coordinate becomes intervals of constancy. And thus, if you use this capital L to time change capital N, which is another arbitrary Markov process, what you get is something which remains constant between the point in the range of this external process sigma. So essentially, we are constructing a process which is continuous, because this guy here is increasing, and thus capital L is continuous. And it has the value of a Markov process, which is kept on a random time. And the random time is determined by the jumps of this object here, this process sigma. So essentially, we are constructing a process which leaves point where it is constant continuously. Okay, so we are taking a Markov process and we are randomly stretching its path. So we are introducing a delay randomly chosen in the evolution of the Markov process. So in order to introduce this more rigorously, be patient. This is a couple of slides of math. I need to introduce the concept of Bernstein function, which are essentially functions which are non-negative, non-convex, and whose derivative is completely monotone. But what is important is that a function, to be a Bernstein function, must be represented in these ways, and vice versa. So this is the class of Bernstein function is in one-to-one correspondence with the class of functions having this representation. And so given A, B, and a measure, you have one Bernstein function, and any Bernstein function is associated to one process sigma, which is the one we are interested in. But later we will always work with this guy here, A and B 0, so you can forget about the meaning of this quantity and just recall that this quantity here, this measure here, will be considered as an infinite measure, so that this integral is convergent, and it is related with the height of the jump of the process sigma. Okay, so the height of the jump of sigma, and thus the length of the interval of constancy here. So we take capital L, the inverse of this process sigma, which is related with the Bernstein function above, being the Bernstein function is Laplace exponent. Okay, so this is the reason why I introduced the Bernstein function. And under, of course, given any Bernstein function, there is a process sigma, which is called the subordinator. And given any subordinator, then there is a Bernstein function such that the equality is true. And under our assumption, we will always have that this process sigma is strictly increasing if pure jumping. So the inverse is continuous and non-decreasing, and it is an absolutely continuous random variable for any fixed t. So if you take a process, a Markov process here, like the one we used in Leaky integrated fire model, and then we time change with this capital L, then we suppose independence on the true process. What we get is that this time changed process, which is the solution when we choose X to be capital V, so often in the bed, to the SDEs introduced above, then this process here is semi-Markov, is a semi-Markov process, okay, exactly as above. And what we did concerning this process is to give an approximation. So we estimated the distribution of the first passage time to a constant ratio. So the result here looks to be difficult understanding. But let me start from the easy case. The easy case is this one. So suppose that the process before as a first passes time to a threshold, which is with finite expectation, okay, like in the Austin-Uhlenbeck case. And then we perform the time change, and this function here represents the time change. Okay, choosing this function here, we are essentially choosing the process which introduced the delay or the random time change in the evolution. Then this new process has a first passes time. The time change process has a first passes time, which is this calligraphic T, whose tail behavior is determined uniquely by the function phi. So the process we are using to introduce the delay. So essentially, deciding which is the random time change, we are deciding what is the decay at infinity of the survival function of the first passes time. Then the original process affects the tail behavior, in this case, only with the constant in front of it, which is the original expectation, which is a number, okay, a parameter. In the case of Austin-Uhlenbeck, then here there is theta, so the quantity appearing in the SDE, in the RC circuit. The general statement is just more general about this, but of course, if the expectation of the original Markov process is not finite, then it affects the behavior of the waiting times even later, even after the time change, and so the behavior at this form. And G is the behavior it's the behavior of this function here. Okay, so it is determined by the original time change, by the original Markov process. Sorry. So some examples. In Brownian case, we have this. So if we are time changing the Brownian motion, we have this for any boundary C. If the Brownian motion starts, this is Brownian motion with drift. If the Brownian motion with drift starts at 0, then we have this behavior of the survival function. For a standard Brownian motion, which has infinite expectation before the time change, then the behavior after the time change is given by this quantity, and here appears the effect of the delay. So the function phi is here. For the time change of the Austin-Uhlenbeck process, so time change of the classical Leaky integrating file model, what we get is by making this choice of time change, so introducing this parameterization, is that the tail function of the first passes time through a fixed threshold have this nice behavior, which is exactly a power law for alpha in 0, 1, and C is a parameter which depends on theta, the original parameter theta, and so you can essentially to make these things fit data, you can just tune alpha and you can tune the parameter C of theta, and you have exactly a tail behavior, exactly the tail behavior suggested by Bernstein and Vandenberg. And you have a model which essentially the same interpretation, okay, because it is just a reparameterization. And the reparameterization is due to the time change, the random time change. What we did is then to estimate also the behavior at 0, and to estimate the behavior at 0 in order to check that what happens to the time change, to the distribution after the time change close to 0, not only when t is to infinity. So we estimated this quantity at 0. Okay, the distribution of the first passes time through a level when t is close to 0. And this is again as above, maybe hard to understand, but this is a bit easier. What happens in this case is that if the original behavior before the time change, so before the delaying, this quantity here goes to 0 faster than any power, then it still do this faster than any power after the time change. Okay, so this is what it is needed in the context of the time change of the Austin-Uhlenbeck process. This is just the general statement. Okay, so if you have the behavior at the before the time change is this behavior with this capital F function, then after the time change, the time change is affected by introducing this rescaling here. Okay, so I told you before, the last thing, and then I finish. I told you before that Markov processes were suitable and were comfortable, because if you don't have information on the first pass time distribution, then you could solve a PDE numerically. Okay, so you can write a PDE using a generator. Then you can always find an approximation about this, about the distribution of the survival function, okay, because it satisfies a PDE. And what we believe it is true, and we have something more that I conjecture, even if this result is not published, is that this is true also in this case. But the PDE is not local. The PDE is given by is given by this form here, and it is non-local in the time variable, in the sense that there is an integral differential operator appearing on the left-hand side. But this guy here is not hard to be dealt with numerically. Okay, so this is something which is still not proved. But what we, okay, there is a mistake here. It is bigger than, not less or equal to, I'm sorry. So the survival function satisfies this object here. And so also in this case, if you are working with a time-changed process and you don't have, and you want some precise information about the tail behavior or about the distribution for fixed t and x, you can still use the numerical approximation approach of PDEs.
Bruno, it's time.
Yes, okay, I finished. Thank you for your attention.
Thank you, Bruno. And we have really a few minutes for questions. Does anyone has a question? You can type in the chat and I will read, or you can switch your microphone if you are connected using Zoom. No comments. I wanted to only underline that you spoke about heavy tails, saying that Markov models do not exhibit heavy tails, and you are right if you think to a constant boundary, but if you think to time-dependent boundaries, you can get heavy tails.
Yeah, sure. Yes.
It's a different perspective.
I also agree with this assertion when the boundary is constant, but what it is difficult to me is to find a parameterization. So as far as I know, you should find a family of Markov processes with a tail behavior which is power law, whose decay alpha is the same parameter of the family of Markov processes. This is something which is hard to do, which I am not able to find. Maybe with your approach, you could introduce the parameter in the boundary, and then you have parameterization of the boundary, which induce a parameter alpha in the decay. This is possible. Yes, maybe, but we are not saying just that Markov process cannot have a heavy tail in the passage time. Yes, of course it can, but with which parameter? Like, can you parameterize the decay?
No, you are right.
Something I'm not sure is possible.
I agree. Yes, you're right. In this sense, I understand. Any further comment or questions? No. Otherwise, we thank Bruno again.